lecture 40. This is the last example that we're going to do with the continuous time Markov chains. This is called the competition model. Okay, the competition model is basically one of the best known competition models. It deals with interspecies competition. So basically, if the species interact, then the population size of the species will decrease whenever the competitor is present. So the typical ODE model is given by this equation. So here x1 is one of the populations, x2 is the other population. So here we're looking at the change in x1. It has some kind of birth rate, so this A10 x1, but whenever it's together with itself, it's going to have competition, and whenever it's together with the species x2, it's also going to decrease. Similarly for x2, it has some kind of birth rate, but it competes with x1 and also itself for resources. Okay, so this is an example of a simulation of the competition model given parameter values for A10, A11, A12, A20, A21, and A22. So this is what the deterministic model looks like. So again, how do we come up with the stochastic model? And so this kind of shows more than what it's supposed to right now. But how do we actually contain the stochastic model? So what we want to do is we want to look at what happens during small periods of time. So we want to look at what's the probability that there's only one transition that happens during a small period of time. And so we have to think about, whenever we're doing this, what are the different transactions that could happen. So here we're letting capital X1 and capital X2 be the random variables that stand for populations 1 and 2. So what we're looking for is now we're going to have two species, and so we're looking for the change in our x1 and the change in our x2, given some current value for x1 and x2. So the different things that could happen, if you're thinking about a small period of time, you can think about, well, I can increase population 1 by 1. And so that would be the only thing that changes. So I want to keep population 2 the same because I'm thinking about only one thing can happen at a time. So I can only have one change effectively at a time. So then the other thing that could happen is, well, I can increase population 2 and x1 stays the same during my small time interval. And then the other thing that could happen is I could decrease population 1 while x2 stays the same, or I could decrease population 2 while x1 stays the same. And then of course we have that during that small increment of time that you could basically stay 0, and we have that there's infinitesimal chance of two things happening at once. So here, the biggest thing whenever you're dealing with more than one category, which is what you're going to be looking at in your homework, when you're dealing with more than one category, you have to think about one transition at a time. So with the SIS model, you had, whenever you had something increasing, then remember you went from S to I, right? So whenever you had something increasing, if the I was increasing, then the S was naturally decreasing, because the only way you can increase I is by coming from S. In this model, however, the thing that's different is I could have an increase in x1 and nothing happens to x2, or I can have an increase in x2, nothing happens to x1. Similarly, I could have a decrease. So just because, so normally I have decrease whenever the population is present or the competitor is present, because they're competing for resources, but it doesn't mean that I'm going to, if I decrease in x1, that my x2 is going to increase. So that's why we look at all of these separately. Okay, so let's look at our ODE. So our ODE gives us an idea of when are we going to have a positive, when we're going to have a negative. Okay, so we want to know for our first transition, when do we get I increasing by 1 and j being 0? So this means when is our x1 increasing is basically what we're looking at. Well, the only time it's increasing, the only time it's positive is here. Our rate would be A10 times x1. So what we have is, if we look at the probability of x1, the change in x1 being 1, the change in x2 being 0. This happens at the rate a10 x1, and the probability would be that rate times delta t plus order delta t. We do the exact same thing for our other ones. So here now if we look at our x2 increasing by 1, then the only way that x2 can increase by 1, this is our only positive one, so we're going to have a20 x2 times delta t plus order delta t. Now how can we lose 1 for population 1? Well, this is a minus sign, so this means it's going to be decreasing. This is a minus sign, which means it's going to be decreasing. So here we're going to have these two things multiplied by x1. So what we have is the probability that x1 is going to be negative, change in x1 is going to be decreasing by 1, x2 stays the same, would be x1 times our a11 x1 plus a12 x2 times delta t plus order delta t. And then finally, what's the probability that x2 is going to decrease? Well, here's our negative and here's our negative. And so there we go. So the probability that change in x2 is negative, we're going to have this here, our rate times delta t. So putting it all together, we basically have this, and so the probability here, the biggest thing that we haven't seen is probability that stays 0 is 1 minus basically all these probabilities that something happens times delta t plus order delta t. And there's infinitesimal chance of anything else happening during some small increment of time. Okay, so the main bulk of the competition model, this is what is on D2L. The main bulk of the competition model, basically we keep going to one of our populations go to 0. Here now we have several different rates, right? So we have several different rates of what can happen. And our R is the sum of all those rates. Take a draw from an exponential distribution to figure out the time that we're going to increase. Here we draw from a uniform distribution in order, so here we draw from a uniform distribution in order to figure out which one of these transitions happen. And then we go transition one by one. So there's 4 possibilities here. That's why we have these 4 different statements. So if our random number is less than our first transition here divided by the sum of all of them, then we're going to increase x1 by 1. And then, of course, obviously x2 stays the same, so this is our 1, 0 case. Here is our 0, 1 case in which our second transition stays the same. So here what we're going to do is we're going to take lambda 1 plus lambda 2. We want to look for R2 less than lambda 1 plus lambda 2 because basically we want to say that the only way that the next thing's going to happen is R2 wasn't less than lambda 1, so it has to be less than these first 2. And then our second one will increase. So then if we have the sum of these first 3, and our R2 is less than the sum of the first 3, and then what we're going to have is we're going to decrease x1 by 1 while x2 stays the same. Otherwise, we're going to decrease x2. And then we update the time. So this is what our realizations look like. So again, I've plotted the deterministic model with it, so you can just kind of see the variation. Obviously, the stochastic model does show a lot more variation, as you even saw in Module 1, than does this deterministic model. So here, we really want to get an idea of what is our Libertine distribution. So with this one, we can't really write down our Q matrix, our generated matrix, easily because we have 2 different populations. And so different things can happen, so it's kind of hard to figure out how to write down that Q matrix. So what we do instead here is we can just do a histogram. So take that final time and keep track of what our population is at that final time when we're done. So keep track of both of these, and then just remember what we did early on, just draw a histogram for them. So what you have here is that this is our histogram at our final time of our x1 and our x2. You can also use the commands in MATLAB to find the mean and the variation about these. So here, the mean is right about what we saw with the deterministic model, right around the 50 mark. But look at how much variation you have, right? So the variation, It's quite a bit. Here are the mean, and here's the variation. Okay, so the next time I'll be introducing Project 2. So basically Project 2, you're going to look at, kind of like you did with Project 1, you're going to kind of think about it as a report. It's not as involved as Project 1 was. Project 1 was a little bit longer than what Project 2 is going to be. But the idea is to actually model something. So you're going to be modeling the spread of a disease. And so we'll talk about that when I put up Project 2.